All right, well, hello everyone. I'm going to be looking at a quick concept video here where we talk briefly about the one of the homework problems that was due. And this is the homework problem where we're looking at the free body diagrams and the action-reaction pairs associated with this situation where we have a brick lying on a cushion that's sliding along the horizontal surface of an icy parking lot. And it's sliding in such a way that the velocity of that system is constant. So we'll start with the first basic idea of drawing the free body diagram. We'll start with the brick. So the brick has, oops, grab my brush. The brick, if I analyze that and I look at the forces that act on it, first of all, I know since the velocity is constant that there's no net horizontal force, and it doesn't discuss that there is any push or pull that's coming from outside of the system. So we're going to assume then that there are no horizontal forces here. And that's a pretty good assumption because if there were horizontal forces acting, then the velocity wouldn't be constant. It would be traveling with some acceleration horizontally. So if I look at the forces that act, first of all, there's a force of gravity which acts on the brick. And this we label as the weight. So we'll just call that the weight of the brick in this case. We could also label it gravitational force on the brick due to the earth because the earth is doing the pulling here. And then in addition to this weight, there's also a supporting force that the cushion exerts on the brick, which we call the normal force because it's perpendicular to the surface of the cushion that's exerting it. So we'll call this the normal force on the brick due to the cushion. Okay? So on the brick due to the cushion. So these are the forces that act on the brick. Now if I look at what the cushion has acting upon it, okay, so here's our cushion. Okay, so what are the forces that act on the cushion? Well, the Earth is exerting a gravitational force on the cushion as well. So that is, of course, going to be the weight of the cushion. Okay, and that's downward because the Earth is attracting it. So here's the weight of the cushion. And again, I could label this as the gravitational force on the cushion due to the Earth. So there's no problem there. All right, then also the brick is pressing against the top surface of the cushion. So I'm going to label that force. I'll give it it's a normal force again. And this is the normal force on the cushion due to the brick. I put a little comma there, but I don't really need it, I guess. But there's the normal force on the cushion due to the brick. So, and then also there is a force that is acting on the cushion because of the surface, the support that's given by the icy parking lot surface. So I'm going to call that the normal, and it's upward. Okay, because that's the support of the parking lot, and this is going to be the normal force on the cushion due to the ground or the ice or something like that. So these are the forces that act on the cushion. And then if I ask myself, okay, and this ends up being then part C for the problem, it says, okay, well, what are the action-reaction pairs in this system? Well, there's many, but a lot of them aren't listed in our diagram because some of the ones that are exerted by, we don't mention the forces that are exerted on the Earth by these objects. So of the forces that are listed on our free body diagram that are action-reaction pairs, the only ones that actually are an action-reaction pair that are governed by Newton's third law is the normal force exerted on the brick by the cushion and the normal force exerted by the cushion on the brick. So that's the only pair of action-reaction pairs here. I saw a lot of folks that had that placed down that, well, the action-reaction pair of the weight here is the normal force on the cushion or something like that. I want to mention that action-reaction pairs always have to be the same type of force. If a gravitational force cannot be an action-reaction counterpart to a normal force, they could be equal and opposite, that's true, but they're not an action-reaction pair. They can be equal and opposite like they are in this case. The weight of the brick is being completely balanced by the normal force exerted on the brick by the cushion. These are equal and opposite, yes, but they're not action-reaction pairs because they're different types of forces. This is a normal force of contact. This is a gravitational force exerted by the Earth. So they're not action-reaction counterparts. This one and this one are the action-reaction counterparts in our diagram, and no others. Other examples of action-reaction counterparts here that would be in the system but aren't shown in our two free body diagrams is there is a normal force exerted on the ground by the cushion, the action reaction pair of, counterpart of this force. There is also, there's a gravitational force exerted on the brick by the earth, but there would also be a gravitational force exerted on the earth by the brick. Both of those would be gravitational forces. But that's the important point that I wanted to get across here, is how action-reaction pairs arise, and the fact that they need to be the same type of force. They can't be different styles of forces. I can't have a normal force and gravity being action-reaction counterparts. It can't be. And the same is true for, say, a frictional force and a normal force. They are not, can't be action-reaction counterparts because they're different forces. One's friction, one's a force of support and contact. Okay, hopefully that helps. Thanks.